Welcome back to the lecture on radioactivity. This is part 5. Today we are looking at half-life. Half-life. As you can see, half-life is the time taken for half the total number of atoms present in a sample to decay. That is the time taken for 1,000 atoms to become 500, or the time taken for 1,000,000 atoms to become 500,000. In other words, the time taken for the total number of atoms to be halved. This is what we refer to as half-life. Let's look at this simple illustration. You have N0, that is the original number of atoms present. And then since nothing is happening, we say we have time T0. The time taken for these to become half, that's N0 over 2, that will give us half-life represented as T half. The time taken for N0 over 2 to be halved again, so if you multiply this by half, that will give you N0 over 4. That means you have halved this to get N0 over 4. That will give you 2T half. If you half it again, that's multiplied by half, that will be N0 over 8. That will give you 3 half-lives. If you half this again, that's N0 over 2, that's 16. That will give you 4 half-lives. So if you take a look at this, N0 over 2 is like saying N0 over 2 raised to the power 1. N0 over 4 is like saying N0 over 2 raised to the power 2. N0 over 8 is like saying N0 over 2 raised to the power 3. N0 over 16 is like saying N0 over 2 raised to the power 4. So if we take this out, N0 over 16 is 4 half-life. N0 over 2 raised to the power 4 is 4 half-life. So we have N0. Let's represent the 4 there with N, small letter N. So we represent this 4 here with small letter N. We represent this 4 here with small letter N, where N is the number of half-lives. This formula is very instructive. We'll use it later on. This will take us to decay constant. Decay constant. We're looking at terms used during calculations. So decay constant, the symbol for decay constant is the symbol here called lambda. And the relationship between half-life and decay constant is given as T half 0.693 over lambda. So T half is called half-life measured in second. Lambda here is referred to as decay constant measured in per second. This will take us to another important formula that is used during radioactivity. N is N0 base of natural log raised to power minus lambda T. The N there is number of atoms present after decay. N0 is number of atoms present before decay, that is the original number of atoms present. Lambda there is decay constant. T is time taken for the atoms to decay from N0 to N. E is the base of natural logarithm, and it has a value of 2.718. This will take us to another formula, that is our decay constant is number of atoms disintegrating, decaying per second all over total number of atoms present in the source. We can take a summary of all the formulas now. So let's take a summary. Quick summary, quick exam summary. That is summary of formulas that you can use for SSCE, WAEC, NECO, or JAMB. Let's look at the first one. Quantity to find, and then what formula? And suppose we are told to look for remaining atom. Remaining atom. We will use N equal to N naught, natural base of natural log raised to power minus lambda T. If we're told to look for decay constant, we use lambda 1 over T natural log N naught, that's original number of atoms present before decay, and number of atoms present after decay. We can also say that our decay constant is lambda is 0.693 over our half-life. The third one now, time. If we're told to look for time, at time T is 1 over the decay constant natural log of N naught over N. Original number of atoms present. If we're told to look for original number of atoms present, we can take N naught equal to N times 2 raised to power T over T half. Original mass of atoms present, M naught equal to M times 2 raised to power T over T half. We need to commit these formulas to memory so that when we come across problems, it will be very easy for us to solve problems.